Swayam Prabha. Digital India. Educated India.
Hello and welcome to the fourth lecture in this course Introduction to Robotics. Today we'll be studying about homogeneous transformations. Now in the last class we talked about rotation matrices, and the rotation matrix is a 3x3 matrix that relates the coordinates of a point in a rotated frame to that of the reference frame. Today we'll look at the cases where if this frame is rotated and also translated with reference to the reference frame, then how do you express the coordinates of a point, okay, with reference to the reference frame. So let's proceed. So today we are looking at homogeneous transformation matrices, and before I proceed, I will just very quickly revise what we were doing in the last class. So in the last class we were looking at rotation matrices. So the rotation matrix is what we derived in fact geometrically in the last class, and very briefly going through the rotation matrix. If you have a reference frame which is given here, so this is my frame A, which is the reference frame, fixed frame which does not move x, y and z, and suppose I have another frame which is rotated with reference to the z-axis. So like this, it is rotated by an angle theta, okay, and this is my frame B, x, y, z of B. This is x, y and z of B. Now suppose we have a point here, let's call it the point P, okay. Now this is my point P, okay, that's the vector BP, right? So now because this point can be expressed in two frames, there are two reference frames here. In the frame B we call it BP, and we say it has coordinates x, y, z, sorry, it has u, v, w, and the same point P, when it's expressed in frame A, then it will be called AP, which is equal to x, y, z. Now because frame A and frame B are rotated, frame B is rotated with respect to frame A, the coordinate of x, y, z and u, v, w will not be the same, okay. So now let us see what does this mean. This basically means that we have this vector here. Now what is the meaning of x, y, z? The meaning of x, y, z is projection of this point on the x-axis of A and the projection of that. So this is my x, that's my y. Now what is the meaning of u, v, w? U, v, w means the projection of this point on the x-axis here and the projection on the x-axis there. Okay, this is the meaning of, so that's my projection. This is the meaning of, this is my v and this is my u. Okay. Now I want to find the relation between x, y, z and u, v, w geometrically. Now geometrically, if I make this construction, I just make this construction here, and this is my angle theta. So if this is v, this side is also v, right? Now if I look at this figure, what we see is that this distance is equal to x, and this full distance from here to here is equal to u cos theta, okay. So it is cos theta. So I can write geometrically x is equal to u cos theta minus this much distance. So how much is that much distance? That is equal to, so this much is equal to this much, which is equal to v sin theta, okay. So x is equal to u cos theta minus v sin theta. And what about y? Y is equal to, where is y? Y is this full distance, full length there, which is equal to, if I make this construction, it is equal to this length plus that length. So this length is equal to how much? This length is equal to this length, okay, which is equal to u sin theta, and the top length here is, sorry, the top length here, this much is equal to this much, which is equal to v plus v cos theta, okay. And what about z? Z is equal to w, because there is rotation about z, so there is no change on z. So now we have derived our rotation matrix in terms of, if I write this in terms of matrix, this is equal to cos theta minus sin theta and sin theta cos theta. This is 0, 0, 1, and that is 0, 0. And on here we have u, v and w, okay. So this matrix is my rotation matrix, which is represented as z theta. Now I insist that you derive this matrix by yourself geometrically like this, the way I've shown. It's very, very simple. You can derive it anytime. So you don't have to remember and by heart this matrix, okay. And if you know this matrix, that's enough. You don't actually need to know anything more, okay. Now similarly, we can also derive the rotation matrix about y and about z exactly x and y exactly in the same way. Now, some important properties of this matrix, let's look at it, which are very important from this in the study of robotics. So our rotation matrix R Z theta was equal to cos theta minus sin theta cos theta 0 0 1 and 0 0. Okay, so this is something that was our rotation matrix. Now this is a 3 by 3 matrix, so it has 9 elements. Okay, but there are 6 constraints. Now what are those? We have seen that each of this is actually a column vector representing x, y, and z. So this is the reference, this is the x-axis of B with respect to the x, y, z of A. Similarly, this is the y-axis of B, and this is the z-axis of B with reference to the x, y, z of A. Okay. Now these are column vectors, so I can say that mod of x is equal to mod of y is equal to mod of z is equal to 1. Okay, why? Because these are column vectors. Again, why? Because these are axes which are unit vectors in 3 orthogonal directions. That is the way we have set up our frame, or that is what we mean by an axis system. The other two are the dot of x and y is equal to the dot of x and z is equal to the dot of y and z is equal to 0. Okay, so we have 6 here, 6 constraints here. So to represent rotations in space, you need 9 minus 6 is equal to 3 parameters. Okay. Now these 3 parameters, remember we are in Euclidean space, so we actually have 3 parameters only. Okay. So if you want to represent rotations in Euclidean space, these 3 parameters of the Euclidean space are taken off. You don't have any more parameters. So you need to move from 3D space to 4D space now. So 3D Euclidean space has 3 parameters, and we need to move from 3D to 4D homogeneous space to represent translations also. So this is taken off by the rotations, the rotation matrix. So if you want to have rotation and translation, you need to move from 3D space to 4D space, and that is what we call a homogeneous space. Now let's try to understand how we move from Euclidean space to homogeneous space. Now let's look at this example and try to understand. So we have a axis system here. This is my reference frame A. Okay, this is my x, y, and z. X, y, and z. Now we have another. Let's put red color. So we have another axis which is here. Okay, so this is my other axis which is B. So B is x, y, z also. Okay, there is no angle between them and the origins are the same. Now if we have a vector here BP, we call this vector BP. Okay, now what we do is I move the axis B, I translate the axis B, the origin of axis B by some distance and see what happens. So what is going to happen is that now if I translate it, what is going to happen is my axis A is going to remain here only. This is my x, y, and z. Okay, so this is my x, y, and z of A. Okay, so from here I'm going there now. Now what I have done is I've translated this axis B by some distance, so it has gone here now. Okay, my vector BP is here now. This is my frame. There is no rotation between them. Please note that x, y, and z. Okay, now suppose I want to find out what is A, what is this vector BP in the reference frame A. How do I do that? So basically what we see here is that it is basically moved by a distance. Let's call this is my z. So what is the distance by which the origins have moved? The origins have moved by this distance. From here the origin has gone there. Okay, and then it's my BP. So if I call this this vector now A, P, B, ORG, meaning is P is the point and ORG is the origin distance between the two frames A and B. That is the meaning of A, P, B, ORG. So how do I find this one now? This is AP. Okay, how do I find that? This is my AP. Okay. So AP can be found as AP is equal to APB ORG plus BP. Okay, now we can add it like this because there is no rotation between the frames. Only the origins have been moved, have been translated by some distance. Okay, now in matrix form, if I were to write this, how am I going to write this? So you can see that in matrix form, what I can do is I can write it as, okay, let me write this on top. So I can write the matrix down here. AP is equal to APB ORG plus BP. Okay, now in matrix form, if I write AP is equal to XYZ, okay, and I have 4 by 4 matrix now, 1 0 0 0 1 0 0 0 0. Okay, this is equal to 0 0 0, this is 1, and here I have the distance by which APB ORG has moved, which is equal to, let's say, QX, QY, and QZ, and here I have U, V, W, Y. Okay, so now you see this matrix is actually, I've written this equation in this matrix form. Now what is X? X is equal to, when I multiply it out, is equal to U plus QX, right? So this fellow has coordinates U, V, W. Okay, so what will happen to X? X is what distance? X is this distance. Okay, that is my X on the X axis, which is equal to this distance, which is here to here, plus that distance, which is U. So this is my QX, and that's my U. Okay, so when I open it, X will be equal to U, which is this distance, okay, on frame B, which is this much, plus QX. Okay, so this is my QX, right? Now what about Y? Y is equal to, how much is Y? So Y is here, right? Y is right up there. So Y is equal to this distance plus that distance. So how much is this distance? This distance is equal to U, is equal to V. Okay, and what is this distance equal to? It is equal to QY. That is the distance in the Y direction between the origin from here to here, right? Now what about Z? Sorry, there is a 0 0 1 here. Sorry, please note this is 1. What about Z? Z is equal to, what is Z equal to? Z is equal to W, okay, plus QZ. Okay, so Z is equal to, if there is a motion in the Z direction, this was rotation, the way I have shown it, there is no rotation, so it is going to be Z is equal to W plus QZ, right? So basically what we are seeing is that we are having a 4 by 4 matrix now here, which is representing, which can transform the coordinate of a point expressed in a rotated frame to that of the reference frame. Okay, this is very geometrically I have shown it, and by looking at this, we can understand that if you want to map the coordinates of a point in a rotated system to that of the reference system, you need a 4 by 4 matrix, and this 4 by 4 matrix is called the homogeneous transformation matrix. 4 by 4 matrix is called the homogeneous transformation matrix. Okay, now we have only rotated. In the previous case, I did not rotate the two frames, I only translated it, okay, because of which there is no rotation, so this is an identity matrix here, okay, because there is no rotation. Now suppose we have two frames. Now the frame B is rotated and it is also translated. So let me draw it here. So this is my frame A, the reference frame. So this is my X, Y, and Z of A, and I have the frame B, which is here now. Okay, this frame B is now also rotated. This is my frame B. So this is X, Y, and Z, but it is rotated. So I have the vector BP here now. Okay, so now we have two frames which are translated and also rotated. Translated means there is a distance between the origins. So what is the distance between the origins? The distance between the origins is this distance between the origins of the two frames. So this is my APB ORG. Okay, now what is BP? BP is having the coordinates U, V, and W. Okay, now if you want to find what is BP in coordinate A, basically means I need to find this vector. Okay, this is my AP. That means point P in frame A. So basically how we can find it is equal to AP is equal to APB ORG plus BP. Okay, so something to note here carefully is that when I wrote this equation AP is equal to APB ORG plus BP, I make the assumption that there is no rotation. Okay, there is no rotation between the two frames. Okay, that is something that is to be noted. Now, if there is rotation, then what we need to do is I need to align frame B along with frame A before I can add the vectors. And how do we do that? We can put a rotation matrix there, ARB, which is the rotation of B with respect to A, and multiply that with BP. Okay, so now what this part will do is it will align B, the axis of B, along with A. Okay, so now if I write this in matrix form, it is going to become X, Y, Z. 1 is equal to, this is my UVW. Now this has 4 parts. This is my rotation matrix. Okay, this is my rotation matrix. This is the distance between the origins, QX, QY, and QZ. This is 0, 0, 0, and this is 1. Okay. Now, if you are saying we have a rotation about the Z axis, suppose for example this is an RZ theta, then this rotation matrix XYZ1 will be equal to cos minus sine cos 0, 0, 1, 0, 0, 0, 0, 0. This is my QX, QY, QZ. This is 1, and this is UVW and 1. What is QX, QY, QZ? That is the distance between this APB ORG is APB ORG is equal to QX, QY, and QZ is the distance between the origins, right? Now, this 4x4 matrix is called the homogeneous transformation matrix. So this matrix can relate the position of a point in a frame which is rotated and translated with reference to the reference frame to that of the reference frame. So the coordinate is expressed in BP. We are expressing that in AP simply by multiplying with this homogeneous transformation matrix. Okay. Now, this matrix also has a lot of interesting properties, okay, which we shall look at. So this matrix is a 4x4 matrix. Okay. So this is a 4x4 matrix where this part is 3x3, and it is called the rotation. It's called the rotation part. This one is QX, QY, and QZ, which is the translation part. So this is translation between origins. Okay, this is called perspective, 0, 0, 0, and that is 1. Okay, so this is called perspective, and this is called scale. Okay, now what we basically did was that I took a coordinate x, y, z in Euclidean space, okay, and converted that into homogeneous space by multiplying that with a scale parameter. So x into w, y into w, z into w, and w. So this is 3, this has become 4 simply by adding that one parameter w, which is called scale. Actually, this is called scale. Now this matrix is very commonly used in CAD, for example, and I'm sure you would have used it in several applications. For example, when you zoom, okay, zoom in, zoom out in any application, when you're watching a picture, or in a doc file or in a PDF file, when you're zooming in, zooming out, what you're doing is you're basically changing that w parameter, and what is happening is every point there is getting multiplied with this homogeneous matrix. Now in robotics, we say w is equal to 1, okay, because we want the lens to be same. So making it less than 1 would mean you're shrinking it. If you make it more than 1, means you're increasing the size. That's the meaning of scale. But it's important to note that from 3D, you have gone to 4D, and this is Euclidean space, this is homogeneous space. Okay. Now, so in robotics, we are having, we always have the scale equal to 1. In computer graphics, they can have a scale greater than 1 or less than 1. Now, this matrix is called the homogeneous transformation matrix, and we write it as T. Okay. What does it do? It is relating the coordinate of a point in a frame B. For example, this is BP. It is expressed in UVW. If you multiply it with this matrix, what happens? It will get converted into in frame A. The coordinate will get converted in frame A. Okay. Now, so this is a matrix which is taking care of both the rotations and the translations. Okay. Now let's do a very simple problem, and so that we understand better, and then we'll proceed to see what is the use of this. So this is the matrix that we are going to use everywhere now. In our forward kinematics, inverse kinematics, everywhere this matrix will come. So let us look at a very simple example. Now a frame B is rotated by 60 degrees about z axis of A, okay, and then translated by say 2 units in the XYZ directions of A. Okay, so it says that we have a frame B which is rotated by 60 degrees, and then it is translated by 2 units in the XYZ directions of A. Now, if you are given the coordinate of a point P in frame B as 1, 1, 1, find its coordinates in AP. As I said, that the base of the robot is not moving, so we have to always convert to the base frame of the robot. Now, how do we solve this problem? Let's draw it and understand first. Okay, this is my frame A. Okay, this is X, Y, Z, Y, and Z. Now we have another frame which has been rotated and translated about the Z axis. So this rotations and translation is about the Z axis. So let us understand this. So it has gone here. So my Z axis will still remain aligned because it's rotation about Z, but the other axes are going to change. So there is a rotation this side, and it is rotated by 60 degrees. So one axis will go this side. If you can imagine, one will go this side, one will go this side. Okay, this is my x-axis, that's my y-axis. This is a rotation of Z about Z, and then translation. So this has been translated from here to here, and that distance is 2, 2, and 2 in the x, y, and z directions. Okay, so now we have a point here BP which has coordinates 1, 1, and 1. I need to find what is this vector, okay, which is AP. Okay, I hope the question is clear to you. Now, when you visualize it geometrically, you can understand very easily what it means. So how do we solve this problem? So we simply go back to our homogeneous transformation matrix here and see that XYZ is equal to the homogeneous transformation matrix into UVW1, right? And we know how much is the rotation. It's a rotation about Z, so we know what is the rotation matrix also. So in this matrix, we know what is the translation distance between the origins. So UX, UI, QX, QY, QZ is given. The rotation is about the Z axis. Okay, so we know rotation is about Z. What is the matrix? This will always remain 0, 0, 0. This will always remain 1 in robotics. Okay. Now, so let's write down AP is equal to T A to B. T is the homogeneous transformation matrix into BP. So XYZ1 is equal to our matrix 4 by 4 matrix. So when you start writing it, you can always write this as 0, 0, 0, and 1 to start off because it's always the same. Okay, and then we can fill in the other. So it's a rotation 60 degrees about Z axis. So the rotation is cos 60 minus sin 60, 0, 0, 1. This is sin 60 cos 60, 0, 0, 1. Right? This is my rotation matrix. Now, what about the translation QX, QY, QZ? It is 2, 2, 2. It is given here that the distance between the origins is that. And this is my BP, which is 1, 1, 1, and 1. Okay. So all I need to do is to just multiply it out, and I can get X, Y, Z. Right. So you can multiply matrices. You can find the value of sine, cos, and then multiply, and you'll get your value of you'll get your X, Y, Z. So in this case, we had the coordinate of a frame in a rotated system, and we wanted its coordinate in the reference frame A, and we simply multiplied with that the homogeneous transformation matrix, and we get that. Okay, so this gives a view of the homogeneous transformation matrix. Now, what is it used for is something which we'll have to look at now. That what is this homogeneous transformation matrix used for? That is one. The second more important question is what is its inverse? For example, in this question, I could have given, say, a question. This is question number 1. Let's say exercise number 2. I'm giving you AP. Okay, is given, some value is given. Okay, and I want to find what is BP. Okay, the same thing could have been done, that I give in the same question, I give that the coordinate of AP is equal to some number, and let's say 3, 3, 3, just for example. Okay, and I ask you to find what is BP. So how would you do that? You have to inverse this equation. So BP is equal to ATB inverse into AP. Okay. Now, one way of finding that is you find the inverse of this matrix, okay, the normal procedure. But this matrix has a particular structure. So if you look at the structure of the matrix, you can actually find out an easier way of inverting it, rather than trying to go into a adjoint of T by determinant of T. Now, how we can find the inverse of this matrix? Inverse of homogeneous transform of T matrix. Okay. So how did this matrix actually go there? Okay, how did we derive this matrix? So essentially we have a frame, okay, and we said that both the frames were together, A and B were the same frame. Then frame B was rotated and translated. Okay, so there is a rotation and a translation between these frames now. That's my frame B, and that's my BP. Okay, so there was a rotation plus there was a translation. So if there is a rotation R A to B and you want to invert it or reverse it, what is the meaning of inverse of this transformation T? It means that you bring this matrix, you bring this frame B and align it with frame A again. That's the meaning of inverse geometrically. So the forward transformation is you are going from A to B, which involves the rotation and translation. Now I'm saying you find the inverse of that. So the inverse of this would mean you have to invert the rotation and you have to go backwards from here to here in the negative direction. Okay, then the origins will come together again, right? So APB inverse is equal to R transpose. This we know very easily. So the rotation of B can be, in order to align it with A, you just have to multiply it with the inverse of the rotation matrix, right? So we take care of the rotations by simply inverting, taking the inverse. Now I have to take care of the translation, that is the distance between the two origins. So if you have gone in this direction, I can come back in that direction. So it is plus and I just come minus. Okay. So in the forward direction, it was Qx, Qy, Qz, right? So I can simply say minus of Qx, Qy, Qz. So the origins come back. But note here that it is rotated. Okay, the frame was rotated. So what you need to do is you need to take care of the rotation also. So I multiply this by T A to B inverse or transpose. Okay, so this takes care of the rotation part. This takes care of the translation part. Okay, so the rotation, we bring back the rotation by multiplying with the inverse matrix, inverse of the rotation matrix. The translation, we bring it back by going in the negative direction of Qx, Qy, Qz, but we note that this has been rotated. So we have to put a rotation matrix there also. So we put a rotation into Qx, Qy, Qz. So if you put this, what we get is the T matrix is equal to rotation matrix into APB ORG. Okay, this is 0, 0, 0 always, this is 1. This was the structure of the matrix. Now if I want to find T inverse, what I can do is I take the rotation has to be, my inverse means transpose. Yeah, this is always 0, 0, 0, this is always 1. And what I do here is I take the minus into APB ORG. Okay, so geometrically again, it's very easy to understand. So mathematically we can prove this, but even geometrically it's very, very easy to understand that how did this frame, the red frame B, go there? It rotated and translated. So if you want the inverse of that process, basically you want to now align B with A. Okay, so what you need to do is you need to invert that rotation and you need to come backwards. Okay, so to invert the rotation, we have the inverse matrix. Okay, so we take a transpose, and to make the negative of the translation, we make it minus into the rotation matrix into minus of the translation distance. Okay, so by doing that, the inverse of the transformation matrix is given by this. Okay, so it's very, very easy because this is always 0, 0, 0, this is 1. R transpose is very easy. You just have to take the transpose of the rotation matrix, and here you just have to take the transpose into R into APB ORG. Okay, so now if we are given a problem, okay, so we are given a problem that a frame B is rotated by 30 degrees about Z of A and translated by let's say 2 to 2 units in x, y, z directions of A. Okay. Now if BP, sorry, let's say AP, I'm reversing the question, is equal to 1, 1, 1. Find BP. Okay. So in the previous case, we had looked at this problem where a frame was rotated and translated, and I had given BP. Now I'm saying I'm giving AP. Now you find BP. Okay, you can go in either direction. Okay, because it's an equation. So how do we find that? We basically write AP is equal to the rotation matrix T into BP. Okay, which implies that BP from here BP is equal to T inverse into AP. We are given AP, so we can multiply with the T inverse and find it. So what is T inverse? So BP is equal to T inverse will be the inverse of the rotation matrix. Okay, cos sine. So it is cos minus sine, and on the other side it is 0, 0, 0, 1. So what is the rotation matrix? Let's write it here. Rotation matrix is equal to cos minus sine, sine cos 0, 0, 1, 0, 0. So if I take the transpose of that, what am I going to get is cos minus sine comes here, sine cos will come here, and this is 0, 0, 1, 0, 0. Right? So the diagonal of this will remain same, and only the minus sign will change positions. What about this side? So this side, now we have to take the R. So we have to take the R transpose into, which is this matrix. Okay, which is this matrix. Okay, into what was the distance by which it has moved? It is moved by 2, 2, 2. Okay, so it is 2, 2, 2, and this is equal to 1, 1, 1. Okay, so you need to find this matrix, multiply it with this. Okay, so this is a 3 by 3 matrix, and this is qx, qy, qz. You need to find the values, multiply them, and there's a minus sign here. Okay, so basically what we did is we exactly did this process. I took the transpose of this, then minus of transpose into APBORG. Multiply this, so you need to multiply that out, and that is your matrix. So then we multiplied with AP. AP is given as 1, 1, 1, and we can find BP. Right? Now this is showing us the use of the homogeneous transformation matrix. That means a frame which is rotated and also translated. If you express a coordinate in that frame, what is it with reference to the reference frame? Now, what is the use of this matrix? Let us see. In robotics, we are going to use this matrix. Let's take this example that we have a robot here. Okay, so we have a robot here, and it has a number of links, and there is an end effector. There's a gripper at the end. Okay. Okay. Now, suppose on a table or on a conveyor, we have a part which has been kept. So we have kept a part in here. Okay, and this is a table. Okay. Now, what is known, what is unknown here? This is an interesting question here. So let's say this is the base of the robot, which is base. Okay, and this is the end effector, which is the tool coordinate, which is T. Okay, now I know this vector. How do I know this vector? I basically know this vector because from here I can go there, and from here I go here, here I go here, and here I go there. So what we need to do is we need to assign access to each of the joints, and then find this vector. Okay, then from this vector we can go to the next vector, then I can find this. Okay, so the link lengths of the robot are known. Okay, and the angles are also known. So basically I know what is that position with reference to the base, and if I multiply it in the forward direction, I can go from B to T, or T with reference to B. This is one. The second is, what else is known? We need to know this vector. Okay, suppose this is let's say S. This is S, and this is my frame. Let's call it G. So I'm putting another frame here. So this is my frame X, Y, and let's say Z. Okay, so X, Y, and Z. So we are basically finding frame to frame. So there is also a frame here, X, Y, and Z. Okay, so I know this vector. Okay, So what we have done is we have attached frames onto each of the points of interest, and this is my x, y, and z. Okay. No, z is upwards, x, y, and z. Okay. So we have attached frames to all the joints and the points of interest. Now what is known? I know this transformation from TB to T is known. Okay. So what is known? This one is known. This one is known. Okay. So it is B to T is known. Now this into this one, okay, into T to G is this loop from here to here and from here to here. These are two vectors. Okay. This is equal to what? It is equal to from here to here and here to there. Okay. On the other right hand side, what do we have? TB to S and TS to G. Okay. So this is one loop here, this is another loop there, and they're meeting at that point. Now in this vector diagram, which vectors are known and which is unknown? So this vector is known, this vector is known. We have to measure it and find out what is the distance of the table from the base. Now on the table, this part has been kept, so I also know this vector. Okay. So on this, what is known? Your B to T is known, this is known. Then on this side, B to S is known and S to G is known. Okay. What is not known is this fellow, is this one. So when a robot has to go and pick up some part, it has to find out that vector, okay, and give it to the control system, and the control system will drive the robot end effector from here to the part, then it can go and catch it. Now in this equation, if you want to find what is T to G, then basically what we do is we take it, so T to G is equal to, I take B to T inverse, I take it on the other side and multiply it with T B to S and T S to G. Okay, so we are able to find out what is this vector given here, right? So this is the use of the homogeneous transformation matrix in robotics, that we essentially have to go and catch something which is at a particular distance or wherever it is placed, and the controller has to find this, what is the distance from the end effector to that object, okay, by using this matrix multiplication, the homogeneous transformation matrix, then it can go and catch it. So this is the use of the homogeneous transformation matrix. Now let us look at another example before we proceed. This is an example of how to go from one frame to another frame. Okay, so in this example, in the previous example, what I said is that I know this vector, okay, because I can go from here to here, here to here, here to here, here to here, by assigning axis at all the frames. Now, how do we assign that axis and how do we go is something we'll see. Very simple case first to explain the use of the homogeneous matrix, and then we'll go on to see what is called DS parameters. How do you define matrix? How do you assign axis in three-dimensional space? So let's look at this example of a robot manipulator. This is one link, this is another link, and this is a third link. Okay. Now, I want to find what is the position and orientation of the end effector with reference to the base frame. Now, the base frame, what I will do is I will put the z-axis z0 and z1. z0 is the zero frame is the fixed frame which does not move. Okay, it's the fixed frame or reference frame, so it does not move. And all other correlations we are going to find with reference to the reference frame. So I'm putting x0 and z0. These are revolute joints, so this is 3 revolute joint planar arm. Okay, I want to show how the transformation matrix actually works. So I'm going to, so you can imagine that because this is a rotating, the joint is a revolute joint, the axis is pointing out of the board. It's pointing out of the plane. Okay, so they're in this direction. So the 0 and 1 I put together. This is my z2. It's out of plane. Okay, this is my z3. Okay, next is x. I put x0 here. x1 I put along the link. x2 is along here, and x3 is there. Okay, so now I have put my z-axis, I put my x-axis. Exact details I'll come in the next class, okay, regarding DH parameters. How do we actually assign? Here is just to give you an example of how the homogeneous transformation matrix works. So I've assigned my frames like this. Now what is the joint angle? Joint angle, this is theta 1, this one is theta 2, and this one is theta 3. Okay, so theta 1, theta 2, theta 3, these are the joint angles. So when this manipulator moves, what changes is theta 1, theta 2, and theta 3, the joint angles are going to change. The link lengths are L1, L2. Now let me use some other color. So let me write it in red color. So this is L1, this is L2, and that one is L3. Okay, so there are 3 frames actually. 0 is the reference frame. So axis 1 we are fixing the x1 frame, the 1 frame. On axis 2 we are fixing the second frame, and axis 3 is the third frame. Okay, now when this robot manipulator moves, what will happen? The joint angles theta can change. Okay, that's how it moves. Now what we are trying to do is, I want to find the correlation of the third frame with reference to the 0 frame now. So what do we do? I am going to find T0 to 1, then I need to find T1 to 2, then T2 to 3. Okay, that means from the 1 frame to 0 frame, second frame to first frame, third frame to, and if I multiply all of them out, what I'm going to get is, so let me multiply it out. I'm going to get T1 to 3, 0 to 3, this into that into this. Okay, so each of these T matrices is giving me the relation between 2 axes. Which 2 axes? This is 1 with reference to 0, this is 2 with reference to 1, this is 3 with reference to 2. And if I multiply them out in the forward direction, I'm going to get the relation between the third axis and the 0 axis. Please note there is no pre-multiply here because this is a homogeneous matrix. Okay, so we are multiplying in the forward direction only. We are not pre-multiplying. Now we need to find each of these matrices, T01, T. So let's start off finding these matrices. What are these matrices? Okay, so this is 0, 0, 0. This is 1. Okay, easy way to start. Now the 0 frame and the first frame have the same origin, so they both have the origin here. Okay. Now if there is a rotation of the first frame, so what will happen? It will rotate about the z-axis. Okay, so if it rotates about the z-axis, what will change is the angle between the x-axis will change, right? So if I rotate the first axis, it will come here, for example, just for example. Okay, it will come like that. So what has happened is theta 1 has become theta 1 dashed. It has rotated about z. So my rotation matrix is going to become cos theta 1 minus sin theta 1. It is a rotation about z, so it is 0, 0, 1. It is sin theta 1 and cos theta 1. So I will not write theta 1. I'm shortening and writing, okay, to save space. So it is cos 1 minus sin 1, sin 1, cos 1, 0, 0, 1. Now what is the distance between the origins here? Qx, Qy, Qz, it is 0, 0, 0 because the origins are the same point. Okay, so this is the relationship between the first frame and the 0 frame in terms of the homogeneous matrix. The origins are the same, and if there is a rotation, it's a rotation about the z-axis. Now if you look at the second transformation, that is 1 to 2, let's look at the second frame. So the second frame origin is here. It has moved by distance L1 in the x direction. So this is my x direction, right? So x1 is along this link. So let me rub this off again. Okay, so the origin of frame 1 has moved in this direction by distance L1 in the x direction, x1 direction, right? And if this one, if frame 2 rotates, what will change? This angle 2 will change. Theta 2 will change. That means the angle, it can rotate and come here like that. Okay, so this fellow has changed, right? So when we are making out, when we are writing this homogeneous matrix, again we write 0, 0, 0, 1. Okay, then it's a rotation about z-axis again. So by an angle theta 2. So it's cos 2 minus sin 2. It is 0, 0, 1. It is sin 2. It is cos 2. It is 0, 0, 1. Now what is the distance between the origins? Qx, Qy, Qz. There is a distance of L1 in the direction of x, there is no distance, no motion in the y direction, and there is no displacement in the z direction. Okay, so this is relation of axis 2 with respect to 1. Now what about relation between axis 3 with respect to 2? So it is 2 to 3. What is this matrix? Okay, now let me rub this one off. Okay, so where is the third origin? Third origin is here. So essentially this origin of 2 has moved in this direction and become origin of 3. By how much distance? L2. What is the direction? X direction. Okay, and if axis 3 rotates, what will happen is it will come here like this. So this is my theta 3. So that will change. So this is my theta 3. So it is going to change when link 3 moves, right? So if I were to write the matrix again, it is 0, 0, 0, 1. The rotation is again about a z-axis like this, okay? And the angle is theta 3, so it's cos 3 minus sin 3 cos 3, 0, 0, 1, 0, 0. And the distance is L2, 0, 0. So we have got our translational, the homogeneous matrices between each of the respective frames. So now I want to go from here to there. I wanted that one. So in the previous case, what I wanted is I wanted this vector, right? So how did I go? I went from here to here, here to there, there to there, and there. So each of these joints I'm putting an axis, then I'm finding the relation between the frames. And if I multiply them out, then I go from here to here. Okay, so we have got all the matrices. Now I need to multiply them out. Okay, now what we can do is some things to note here. Okay, please note y-axis. So y-axis is not normally written. Y-axis not written or drawn. Why? Because of the right hand rule. Okay, that means if you fix so fixing x and z automatically fixes y by the right hand rule. So if I have x here, I have this is x, y, and this is z. So the moment I fix this x and I fix the z, this gets automatically fixed as per right hand rule. Okay, so that is the reason why if you look at robotics textbooks, you'll not find y-axis anywhere. So normally y-axis is not indicated, only x and z is indicated. That is one thing to note, okay, in our whatever we have done here. Okay, now another thing to note is that the z-axis was axis of rotation, Okay, now because the z-axis is the axis of rotation, the rotation matrix is always cos minus sine cos 0, 0, 1, 0, 0. This is always the rotation matrix because it's always rotation about z only, and that is the reason why I took z as the same, and it was the axis, the revolute axis was perpendicular to this plane. Okay, and they are assigned as z, so the rotation is always about z. Now if I multiply these matrices, these three matrices, okay, so I'm going to multiply them out. So what I need is t0 to 3, which is equal to t1 0 to 1 multiplied by t1 to 2 multiplied by t2 to 3. Okay, I simply multiply. So first I'll multiply these two. So t0 to 1 into t1 to 2 is equal to, let's go back and see this. You know how to multiply matrices. So it's this row into this column, then next, like that. Okay, we are multiplying this matrix with that matrix. Okay, what do we get? We are going to get cos theta 1 plus theta 2. So I'm writing it as cos 1 2 minus sine 1 2, sine 1 2, cos 1 2, 0 0 1, 0 0. And here I'm going to get, this is always 0 0 0, this is always 1. Out here I'll get L1 cos 1 and I'll get L1 sine 1, I'll get 0 here. You can multiply that and see. Now the meaning of cos 1 2 is equal to cos theta 1 plus theta 2. Okay, similarly sine 1 2 means sine theta 1 plus theta 2. Okay, I'm writing it in short like this. Okay, now if you go back and see, if you multiply, that is what is going to come. So this cos theta 1 minus sine theta 1 into this is cos 1 cos 2 minus sine 1 sine 2, which is cos theta 1 plus theta 2. Okay. Similarly, if you take this into this, you'll be getting the corresponding term. Okay. And the last one, so the fourth term of the first row, this into this, you'll get cos theta 1 into L1. Okay, the others will all become 0. Okay, so multiply these matrices and this is what you'll get. Now I need to multiply this matrix into T 3 to 2. Okay, now let's multiply this matrix into 3 to 2. What was the matrix 3 to 2? So the matrix 3 to 2 was into this matrix. It was cos 3 minus sine 3 cos 3 0 0 1 0 0 to 0 0 0 1 here, and this is L2 0 0. Okay, this is what it was. Okay, so this matrix, right? So I've written it there. Now I'm multiplying this matrix with respect to so I'm multiplying this into this now. Okay, so this is all this side, right? So again, the same way we can multiply this row into this column. So it will become cos 1 2 cos 3 minus sine 1 2 sine 3, which is equal to cos theta 1 plus theta 2 plus theta 3. Okay, and what will happen to the last term? This will get multiplied into that. So it will become L2 cos 1 2 plus L1 cos 1. Okay, you can multiply it out and see. What you'll get is T 0 to 3 is equal to cos 1 2 3 minus sine 1 2 3 sine 1 2 3 cos 1 2 3 0 0 1 0 0 is equal to L1 cos 1 plus L2 cos 1 2. This is L1 sine 1 plus L2 sine 1 2. This is 0. That's my matrix, right? You can verify it. Okay, so cos 1 2 3 means cos theta 1 plus theta 2 plus theta 3. Okay, this is what it means. So this gives us the relation between the third axis to the 0 reference axis. Okay, now is this correct? Or I have been writing this matrix without looking at the previous ones. If you're guessing, if you're trying to guess how am I writing that? Okay, so we have derived this completely geometrically. So there is, once you understand what each of these parts of the matrix mean, you can very easily write them down even without doing all these multiplications. That means if I go to this matrix, if I go to this manipulator, okay, and I want you to find the relation between the third frame and the first and the 0 frame, you should just be able to look at it and write. Okay, there is no need to do all this matrix multiplication. Because the matrix is important, you need to understand how it's working. But apart from the mathematics, geometrically you should be able to understand what actually this mathematics means. And we have seen that what it means in terms of the rotation matrices is very, very clear. Okay, this is a rotation. Where is the matrix? Yeah, here. This is a rotation between the two frames about the z-axis. Okay, this is the distance between the origins. Okay. And this is always 0 0 0, this is always 1. Now once you keep that in mind, then you can very easily go from one frame to another frame. Okay, and you can actually find the final transformation matrix. Now let's come back here and see whether it's correct or not. So we have multiplied all of this and we have got a matrix like this, which is giving the relation to the third frame and first frame. But now let's look whether it's correct or not. For example, if you have a very large manipulator, 10 degrees of freedom, and you're multiplying all of them, you get some very, very big terms. Now, is it correct or is it not correct? How do you know? Okay, so by looking at the geometry, you can very easily find out whether it's correct or not. Okay, so this was my manipulator that I just drew. I'll just draw it again. Okay, and I assigned axes like this: Z0, sorry, Z0 and Z1. So Z0, Z1, Z2, Z3. Okay, this was my X2. X0, X1, this is my X2, this is X3. Okay, this is my angle theta 1, this is my angle theta 2, and this is my angle theta 3. Okay, so this matrix is relating the frame 3 to frame 0. Okay, the question is it correct? Now this is my X0 direction, this is my X0, that's my Y0, and this is my Z0 pointing outward. Now what is this giving us? This part is giving us the total rotation of the third frame with reference to the first frame. Now what is the total rotation of axis x3 with reference to x0? First it rotated by this much, theta 1. Then it, let me change the color to make it clearer. So first x0 was in this direction. Then it rotated by an angle theta and went there. So that's my theta 1. Then theta 1 rotated by theta 2 and went here. Then it rotated by theta 3 and then it went here. So x0, which was originally in this direction, it rotated by theta 1, then by theta 2, and then theta 3, and then went there. And this is what it's showing. It's cos theta 1 plus theta 2 plus theta 3. Okay, that means the x0 axis rotated by theta 1 plus theta 2 plus theta 3 and then became x3. Now what about the origin of this frame 3? This is giving the distance in the qx, qy, and qz. Okay, distance between the origins of frame 3 and frame 0. So is it correct? What is the displacement in the x direction? So this is my x direction. So if I project it on the x-axis, then it is this distance plus that distance. So this distance is equal to what? It's L1 cos 1. This distance is equal to what? This distance is equal to this distance, which is equal to this theta 1, this theta 1, right? So it is equal to L1 cos, sorry, it is L2 cos theta 1 plus theta 2, right? So this is giving us L1 cos theta 1 plus L2 cos theta 1 plus theta 2. What about in the y direction? So projection on the y-axis is equal to this distance plus this distance. What is this distance? This distance is equal to L1 sine 1. What is this distance? It is equal to L2 sine 1 2, right? So this distance is equal to that distance. So geometrically, we see that the distance in the y direction is L1 sine 1 plus L2 sine 1 2, which is equal to qy. And what is the motion in the z direction? There is no motion in the z direction, so it is 0. So it is correct. So simply by looking at this manipulator, we could have written that matrix. There is nothing complicated here. Once you understand the geometry, okay, it's very, very easy. There's nothing complicated in the mathematics. So you have to correlate the mathematics with the geometry and try to understand these transformations and how they work in space. Okay, so today we talked about homogeneous transformation matrix, and I showed how you go from one frame to another frame. So how do you relate the nth frame to the zero frame by means of homogeneous transformation matrices? Now in robotics, there is only this, there is nothing more. So you need to understand this very carefully in terms of the geometry. So we'll stop today and continue in the next class. Thank you.